Here is the, let me say, this is a new section. Let me call it natural frequencies. Single degree of freedoms, vibrating system. Okay, so this will be the first time in we introducing the first important the parameters here. So we consider this system. So say this is a mass m, and this is the spring constant. Okay, and if you like, we can also have such a system. Describe. This is K, and this is M. And again, on the difference of the two examples is this one. We assume we have considered the gravity influence. And however, we know that from the day one, we know when we describe the vibration, we have to describe the vibration in terms of the equilibrium status, equilibrium positions. So that means after we consider the influence of the gravity, due to the weight of this mass, and that weight will cause this spring to deform a little bit. Under that deformed positions, then the vibration will start to vibrate. So for example, say again, the setup is this. Let me use my hand to hold this weight. And right now I slowly, very slowly to release my hands. And on the, we call the quasi-static process. So basically this block going to, due to his own weight, going to coming down a little bit. So these diffractions, let me call the delta ST. Okay, delta ST is the weight caused diffractions of the deformation of the beam, and that basically is equal to mg divided by k. So this is called the equilibrium positions. Of this system. Okay, right now the gravity is here. So right now, if we describe the vibration in terms of such equilibrium systems, so let me use the red one to describe, to emphasize such equilibrium positions. So from here, we define our degree of freedom, xt. So xt is our defined degrees of freedom. So that means if there will be any the oscillations or vibration, the oscillation or vibration will be centered respect to these equilibrium positions. Okay, so that means if this mass block, the maximum displacement is 5 centimeters, 5 centimeters here and then 5 centimeters here, and back and forth vibrating. Not respect to his original undeformed position. No, it starts from the equilibrium position. That is a very important concept. Okay, and go back to read the textbook. There's a few pages of description, and the textbook, the author using very detailed and lengthy discussions, but the same concept is kind of described here. Okay, so for this case, for this kind of horizontal configurations, basically gravity doesn't take any effect. So basically equilibrium positions for this one simply is his original undeformed configuration of the spring. So for this case, we simply say this xt we define is degree of freedom like this. So the equilibrium positions for this case is corresponding to the deformed undeformed configurations of the spring. So basically the spring does not deform, and given that kind of configuration, we define as an equilibrium. Okay, so that is the kind of discussions. So keep those things in mind, for for simplicity, so right now I just taking this as the example here and to save the drawing. So this is K, this is N, and here assuming we take it from equilibrium positions. So from this moment onward, otherwise emphasize, we always start our description from its equilibrium positions, okay? So keep that in mind. This is a very, very important concept here. So we're starting from here, okay, so from the equilibrium positions, we assume the mass has been dragged down a little bit, which means displaced a little bit. So I want to formulate the equation of the motion, okay, so back to the slides a couple of days ago. The first step is to write the equation of motion. To do it, so basically here we assume this mass block being displaced by that much, okay? So that means the mass block being displaced by that much. So according to the degree of freedom, so basically that is the displacement made according to the degree of freedom. So we can just say that is x, okay, whatever the x, and then that is a function of t. Basically that is the degree of freedom here. So we take the free body diagram on this mass block, okay. And due to such assumed displacement, we begin to analyze the distribution of the force on this mass, okay? And right now, given only have one spring, and under such assumed configurations, you can see the spring has been stretched by how much? By x. So the spring has the force existing there, and that force is going to try to recover the springs, configurations. So that means the spring will exert a force on here, and that is actually equal to kx. Okay? This is a force. And right now we're talking about a dynamic system. So using Newton's second law, by using the force equal to ma, and which it is mx double dot. So basically that is mx double dot, right? So what is the directions of the, sorry, I need to draw it. So this one is the m. And according to the degree of freedom x, so basically this is the x and displacement, and that means velocity and also velocity by the accelerations. So in terms of the mass, and the total force equal to mx double dot. And let me define the sign of convection. Say this is my assigned sign convention. I assume downward is positive. So that means this force provided according to sign convention is negative, right? So this is a very simple degree, using free body diagram to analyze and according to Newton's second law. So from here you can see, taking up the two equations, the sign here, then we can have mx double dot plus kx equal to 0. Okay, and this is the second orders linear differential equations. And sometimes, and in my lecture notes, I simply using the brief ODE. So ODE, that means ordinary differential equations. Okay, and in particular, this is a linear ODE. In ME 408, our focus is only on linear system. What means the linear system? The linear system is such that the coefficients of the equation are linear. In particular, these are constant. Okay. So that's the differential equations, and most of the time we can further simplify. So from this moment onwards, we can say x double dot plus k over m x equal to 0. So that is our the equation of motions. Of course, this is also the equivalent equation of motion. The two are equivalent. Basically, they are identical. I simply scale the coefficient of the highest order to 1. Okay? So, pertaining to this particular form, we define our natural frequencies. So, natural frequencies is defined as this. definitions of the natural frequencies and omega n. Okay, the omega n is defined as this. In terms of this template, we define the omega n is such that omega n squared corresponding is the coefficient of the x. So compared to the two terms, then we know that omega n squared equal to k over m. That means omega n equal to the square root of k over m. Right? This is the definitions, and actually later on, once we explore more, we can see this actually is not a definition, that is the mathematical result. But here, before we're doing that kind of the rigorous mathematical review, then here, let me use the words, let me just directly define it. So that means you take it, and later on I will give you an explanation why the natural frequencies look like this. Okay. So with these informations, then we can look at our example here. For such an equivalent system, back to our elastic beam as a model. So for our elastic beams, we have the equivalent description of the system. This is a KEQ, and this is the MEQ, and in terms of the degree of freedom, eta. Right? So again, from this example, we have found the MEQ is such a value here, and KEQ is such a value there. So we have a simple description like this. So are we able to calculate natural frequencies? Yes. So simply plug into here. Natural frequencies simply is equal to, here is KEQ divided by MEQ. Okay. And the equation of motion for this particular example in terms of my parameter eta basically is MEQ eta double dot plus KQ eta equal to 0. Okay, simply swap the symbols to that one. So once we have the MEQ, KQ, simply plug in. So basically we have a lump for elastic beam. For example, if you have a bamboo, you take a very the sling, very long bamboo, and usually in Asian countries, old time teachers, in particular the elementary school teachers, 3 foot long, and pick that one with the teachers. Come over here, you didn't leg turn it, and you can hear the sound and kind of whipping through the air, kind of scary. But that one, actually, that's one example of the elastic beam. Okay, so from here, we lump the whole continuous system into the single lump sum of the mass. So from there, you can very roughly estimate the natural frequencies here. Okay. I was hit until middle school. Actually, then I became strong enough. I hold it. I sacrificed for the first hit and I hold it. Later, I was kind of asking to stand outside. It very hurt. But anyhow, that is the definition here. So using this one, basically here we have the kind of the first taste of the natural frequencies. And using this example, you can see we can really using what we have learned so far to deal with very, I would say, a little bit more complicated practical system like this one. Okay, so we back to our in the section here.